So now we have our official Superbowl of Astronomy poster, and David is going to tell us what happened at the meeting.
Sure. Well, I'm going to give you the highlights. There's thousands of papers that are presented, lots and lots of talks, concurrent sessions. That's why they call it the Superbowl of Astronomy. A lot goes on. But I'm just going to give you the highlights. There's a radio observatory here, and these things called fast radio bursts. They last a very, very short time, microseconds, milliseconds. They seem to be random directions in the sky, and we get 5,000 to 10,000 of these per day. And we don't know what they are. If we go forward, now radio waves do something kind of funny. The blue light from this burst will arrive sooner than the red light. And the further away the object is, the more dispersion there is. The blue light, you'll get it even sooner, and the red light will be even more delayed. It has to do with electrons in the way. So anyway, we know these things are really distant because we can see this dispersion in them. They're all really, really, really far away. We don't know why there aren't any close to us. But we have yet to notice any. There's one out there that repeats, however. All the others seem to just happen and go away. There's one that repeats, and they were able to get an image of the galaxy that this radio burst is happening inside. It's a dwarf galaxy. It's not in the very center of it. It's a little weird. That's how big the Milky Way would be in that image, by the way, if you were to see the Milky Way in that same image. So this is a really small galaxy that's making these bursts, and they're really powerful because they're from very far away. So that's one highlight, was neat. Another high-energy story, they took the deepest X-ray image ever. These are all X-rays, and most of these things are black holes. There are 155 black holes in this image, to be precise. There's about 1 billion active galactic nuclei. That's a black hole in the center of a galaxy, in the entire observable sky from here on Earth, because there's so many in this one frame. If they were to take an equally deep image, we'd see all of those. So that's just insane how many there are. You step forward, you can see they all are in host galaxies. They're able to get distances to most of these. So pretty outstanding work. We go forward to the next story, a fun one. This looks like an absolutely normal patch of sky. This is actually a couple of galaxy clusters that are in there. A lot of these dots are galaxies. Well, the black holes in the biggest galaxies are sending out jets of electrons that are moving at very, very fast speeds, almost relativistic. Well, when those interact with the gas around the cluster, they make radio waves and also X-rays, and we can see those if we step forwards. They took both radio data and X-ray data. The X-rays are blue, and the radio waves are the magenta color there. So pretty cool, they're able to map this out. We step forward, they're using the Voyager spacecraft to actually map. Yes, all right, we have everybody that said Voyager right there at the time come down and get a prize. But Voyager data, if we step forward, we have the most amazing graphic ever. The solar system's perfectly to scale, of course. I'm joking, that's sarcasm. The planets aren't that big compared to the sun, the distances aren't right, but nonetheless, they are using the directions to the Voyager spacecraft, making observations with Hubble, and they're able to measure the densities of electrons, the amount of gas that's out there, and the local interstellar medium looks a little like this, which is cool. The gases, those arrows show the direction the gases are moving, the sun is in the middle, and there's a lot of gas around us in the local interstellar medium. No, but...
Are you on drugs? I'm sorry. I know him, so for the rest of you, I'm really not that rude.
Yeah, you don't.
I'm sorry.
I've been hospitalized for
I know. I just realized people are like, oh my gosh, that woman is so...
Wow, I'm not playing that game.
Exactly. Go ahead, make your guesses.
And get belittled.
Anyway.
All right, but it's pretty neat to be able to see the local interstellar medium around the sun. It's something a lot of people don't think about. And about 10% of the mass locally is in this sort of gas, which is neat. Stepping forward, we're actually getting pictures of the exoplanets. The Gemini Planet Imager has been doing that for a while. A new instrument called CHARAS First Detections is on the Subaru telescope, and these are actual images of exoplanets right there, and a disk. If you step forward, we can see all sorts of images. These were taken by many, many different telescopes. All those little dots around the central blobby-looking thing, the blob is where the star got subtracted out, by the way. All those little dots around it are planets, and the coolest thing, this isn't a AAS result, but I had to include it here. This is planets orbiting a star. So, yeah, they took data over several years, and you're actually able to watch these giant planets orbiting this star. So that's just mind-blowing. We're able to see this sort of stuff. Moving forward, the Sloan Digital Sky Survey is a really pretty old sky survey that measured the whole sky. Well, people have been going in there and still measuring the elements and taking spectra. And of course, the elements we're interested in about life are those Schnapp's elements, the ones that are circled. That's what's important for life. So they were doing investigations and thinking, well, stars of different metallicities, if we step forward, we can see some spectra. If you take the light, break it into its rainbows, the elements in the atmosphere of the star make those little vertical lines. And the more of them they are, the more heavy elements like calcium and carbon and oxygen that are in that star. So the question was, can you have life around a planet that's made of sort of similar things for all these stars? So they did some studies. We can step forward here and see the different kinds of planets that are made. A solar composition, we know you can get an Earth around it. Well, what if you have a different composition? What kind of planet do you get out? Well, they did some models, and it turns out, and we look at the next slide, you can actually make an olivine planet like Earth. Earth has a lot of olivine, and they called it olive, which I think is funny. They called their planet that makes garnets. It has a slightly different composition, Janet. And that one might not have plate tectonics. It might be, the material's a little harder to move, so it might not be so great for life. The atmosphere doesn't get recycled, perhaps. I renamed them their actual names. And then anybody that knows this is Stephen's universe will recognize this. So, okay. All right. Anyway, it's pretty neat to think we're actually doing studies about what the different planets might be like around these stars with the different compositions. So the modelers are really going all out on this. Now, another mind-blowing result here, we actually see a shadow in a disk around another star moving. All right, why would a shadow move? You can see in the bottom panels, the shadow's kind of off in one direction, and then it's moved. A year later, it's kind of moved over, or whatever, 5, 6, 7 degrees, whatever that is. So kind of strange. Well, what could be going on? This is the best model they came up with it. It's actually the disk around the star. It's a planet-forming disk. There is a gap in it at about 1 AU, and they think there could be a planet there that has made a warp in the disk, and that warp in the disk is what's casting that shadow. They made a simulation of what that should look like, and it'll look like this, and it matches pretty well. Well, they based it off the data, of course, but then they said if you have a rotating disk like this, what would it look like? Well, we'll have to compare it in the future and see if it continues to move around this disk like that. But to think we're seeing shadows of a disk falling on itself, kind of amazing. The Milky Way, our own galaxy that we lived in, that we lived in once upon a time. We're no longer living. It's all past tense now for me. Anyhow, galaxy that we still live in.
That's okay. We have some furry bunnies for you later.
The galaxy we're in, we don't quite know the mass of it. It's like being in a forest and trying to see all the trees within the forest. Well, we can use the globular clusters. This is a globular cluster you're seeing here. Very dense objects, millions of stars in them, and they orbit our galaxy. If we go forward, you can see locations of a whole bunch of them. Well, you can use the motions of these to measure the mass of the galaxy. Just like we can use the motions of the planets in the solar system to measure the mass of our star, you can use the motions of these to measure the mass of the galaxy. Well, they did a bigger study, and they reweighed the Milky Way. And the answer was, well, good if you're trying to lose weight. We'll take a look here. It went from about 1 trillion solar masses, was a rough estimate, very big error bars on that, and their better value is somewhere around 620 to 700 billion solar masses. So we lost about 250 to 300 billion solar masses, which is pretty good if you're on a diet. So a new mass for the Milky Way, maybe we're not quite as big as Andromeda. It's a battle. Which is M31 bigger? Are we bigger?
We're not happy.
Well, we'll find out. Well,
how's the cholesterol level?
it's pretty good. Pretty good. Yeah. We've cut down on our eggs, Tony. So. Anyway, and I think that was the main results from the AAS that excited us, and we'll find out what comes next year. So join us a year from now for another round table discussion.